The next topic we want to discuss about is the binary search tree. If we take a look of the big picture, saying that the big frame is regarding to the graph theory, which is talking about the nodes and edges that are connected together. You can see that the tree topic is a subcategory of the graph theory because we want to look into a rooted tree. So everything started with what we call a root node. The tree can have as many children as possible. Inside of the tree topic, we have defined a subcategory of the tree called binary tree. In this case, no trees can have more than 2 children. And by doing so, there's a lot of applications can be applied in computer science theory. Today, we want to look inside of the binary tree and then discuss one more subcategory of the binary tree. So, a binary tree is a node can have no more than 2 child. If we look one step further into the binary search tree, it's basically a binary tree. So whatever we try to discuss today is inside of the binary tree discussion, in which every node satisfies the following criteria. What this is trying to say is that the key, which means the value inside of the node. Previously, when we're talking about a tree or a binary tree, there is no rules about what's the value that we can put inside of the data part. But now we want to discuss about it. The key or the value of every node in the left subtree is smaller than the key of this node. And all the nodes on the right subtree is larger than the key of the node. So what I'm trying to say is, by looking into the root node of 5, all of the nodes, pay attention, not just the left child or right child. It's talking about the whole subtree on the left side has to be smaller than the root. All of the subtree on the right side of the root has to be larger. And this is not only applied on the root node. For the node of 3, you can consider it is the root node of this size 3 binary search tree. All the nodes on the left side is smaller and all the nodes on the right side is larger. So that is the definition of what we call the binary search tree. One question that you may have is that we only talk about all the nodes is smaller on the left side and all the nodes are larger on the right side. So what if we have some duplication values? This is actually, we try to simplify the problem by saying that there is no duplications in the binary search tree. And by doing so, we will not need to worry about when the 2 values are equal together. Of course, we can take care of the assumption if there is duplication, no. If there is a duplication, no. All we need to do by doing the definition is that we just need to choose, we want to put the equal sign on the first criteria or the second criteria. In other words, if there is duplication, no, and we can simply say the key of every node in the left subtree is smaller or equal to the key of its node. By doing so, we can handle duplications. So it's not a big deal, and therefore we choose to ignore that situation, saying that we won't have any duplications. This can be true by doing some ID identification value search, primary key value search, and since those are the things cannot have duplications. So this is, you can see binary search tree is a subcategory of the binary tree, while binary tree is a subcategory of the tree, and tree is a subcategory of the graph theory. This gives you a big picture of where we are working into. So, binary search tree, the left subtree and the right subtree are also binary search tree. What they're trying to say is that not only the root node need to satisfy the criteria of the binary search tree, but also all of the nodes. No two nodes in the binary search tree have the same value. This is what we have discussed. We try to eliminate the duplication nodes. And one interesting thing over here, by combining of what we have learned so far, is that if we try to traverse the binary search tree in order, so you can see that we will go into the root, go to the left side, go to the left side, print it out 1, come back to 3, print it out 3, go to 4, print out 4. That time, all the left subtree is done, come back to 5, and then print it out 8, print it out 9. You will notice that this is actually give you a sorted sequence. And basically, there is actually a name for this sorting algorithm called binary search tree sort. And this is an interesting property which combines of what we have learned previously in our tree topic. Here are some examples, and you can try to apply the idea of the in-order traversal on all of these nodes, on all of these trees. This node, one node, it satisfies all the criteria that we have. So this node, this tree is a binary search tree. This one is also a binary search tree, which is actually in a very balanced format, which is some properties that we like, and we will discuss about this. Look at this left side of the example. This is also a binary search tree because simply by looking into the left subtree, all of these nodes are smaller than the node of 10. All of these nodes are larger than the root. And again, it is not the root that the only node we check. We also need to check all the nodes basically. Node 2 is actually the smallest node of a whole binary subtree. If you look into the left side, there's nothing over there. If you look into the right side, all of the values are larger than 2. So that's good. The node 6, all the nodes on the left side is smaller, all the nodes on the right side is larger. So on the left subtree of this binary search tree satisfies the criteria, and it is also the right criteria to fit for the binary search tree over here. 12, you can see 14, 16, 15 are larger than 12. Good. Node of 14, 16, and 15 are all larger than 14. That's good. 16, the 15 is smaller than 16. So you can see this is also another good example of the binary search tree. You may be interesting. Looking into the right example, is this a binary search tree? The answer is yes. It looks ugly, and it gives us a bad performance on whatever we will discuss later regarding to the binary search tree. However, this is also a binary search tree because the root is 1, there is no left child, all the right child are greater than 1. Good. Node 9, all the left side are smaller. That's good. Node 7, all the left side are smaller. Node 3, all the right side are larger. So this is actually also a binary search tree. So this gives you a counter example. You can see that if we simply look into the node 3, left side is smaller, right side is larger. That's good. However, if we check on the node of the 5, which is our root node, all of the left side except 7 are smaller than node 5. However, 7 throws an exception indicating that this is actually not a binary search tree. So this is a very important thing for you to check every single node need to satisfy the binary search tree criteria. So if we have a binary search tree, what can we do except print it out in order traversal to get a sorted sequence? Another property of the binary search tree lies in the name of the binary search tree, which means that we can do search easily. If we already know the property, all the left side are smaller and all the right side are larger, this actually gives you a very similar concept of binary search, except this is a tree format, and therefore to find a value inside of a binary search tree, we start comparing the value we want to find with the root, understanding that we will travel to the left side or the right side, and we will keep moving until we find a node, or there's a possibility saying that the item is not there. So how would you know the item is not there? It's that when you try to search all the way until you hit a newer node, that means the element is not there. So this is the basic concept of the binary search tree. Saying that we want to find the node of 5 inside of this binary search tree, we compare with 8, understanding 5 is smaller than 8, we will travel to the left side. Compare 5 with 4 is larger, so we need to go to the right child. Compare 5 with 6 is smaller, so we need to go into the left subtree, and there we find a node of 5. So this is how we will be able to perform the search property. And search is probably the most important function inside of the whole binary search tree topic, because almost everything requires the idea of the search. Let's take a look at this. In the abstract data type, we try to define different basic functions for the binary search tree. As we discussed earlier, search function is probably the most important one. Finding minimum and finding maximum are interesting because they are super easy. While we try to do the insert, we need to insert some items inside of the binary search tree and delete, indicating that we want to remove some items inside of the binary search tree while we can still maintain the property of the binary search tree. So these are the 5 major functions defined inside of the binary search tree topic. Let's take a look at this. As we discussed in our previous chapter, tree, we define the node as a node with 1 data part and 2 pointers. Since this is a binary tree topic, we define it as a left node pointer point to the left child and a right node pointer point at your right child. By doing this, all the nodes that are defined inside of the binary search tree to represent this tree structure, we will end up with this, starting with the root, and of course you will need to have a pointer to point at the node of 5, indicating this is the root pointer. You will point to your left child, right child. If there is no left child, you will put a null value, and so for the node 1, 4, and 9, they are leaf nodes, and leaf nodes are the node without any child. So while we try to search a value inside of the binary search tree, what you can see is that we will compare the value with node of the root, which is pointed over here. We will understand to look into the left side or the right side. So let's take a look of the code here. If we want to find a value, x is the parameter, which is the value that we try to find, we would define a pointer equals to root to duplicate the location of where to start. Like linked list, we never want to change the first node because we need to remember where that location is going to be. So we make a pointer equals to the same location of the root, and we will start the search process. While t is not equal to null, while we try to move and it is not hitting the null value, we will need to keep searching. So you can see that in the beginning, we want to find the value of 4. We compare, we say t equals to root. Since t is root, it's not null, then we try to compare the value. We look into the value x, which is 4, compare with t to the element, which is 5 over here. Understanding that it is a true statement because 4 is less than 5, indicating the element we want to find is less than the root. So we need to travel to the left side. So take a look, how do we travel to the left side? We simply say t equals to t to the left. So we will be able to go to this node, node 3. And that is the loop that we can come back. Therefore, you can see there are 3 possibilities over here. One is the value we want to find is less than the element, so we need to look into the left side. The value we want to find is greater than the element, then we need to go to the right side. If it is not less, it is not greater, that means we are finding a value that we are interested in. So you can see that these are the 3 if statements. And of course, we take away the possibility of the duplication nodes so that we would get one value exactly, so that we won't see problems of the duplications. So you can see that when we come back to the loop, compare 4 with the node of 3, we understanding that we're hitting the second else if part, then we will travel to the right side. So t equal to t to the right, which will come to the address of this node. Come back to the while loop. It is not less because 4 is 4, and it is not greater. Then this is where we find the elements that we are interested in. Let's take a look at a special scenario. Saying that we want to search for the value of 2. What's going to happen? So search 2. Node will equal t will equal to the root. So we start searching over here. 2 we compare with node 5. Understand we need to go to the left side. So that's one iteration of the while loop. 2 will compare with 3, smaller, so we need to go to the left side again. In this case, we will compare 2 with 1, understand it's larger, so we need to go to the right side. So 2 is greater than 1, so we need to go to the right side. However, after that's the scenario, we will come back to the while loop, understanding that there is actually no nodes on the right side of value 1, and that is when we would stop the while loop hitting the return null operation, indicating that we have not find the element. So that is how we will be able to do the search operation. For both insert and delete, they require the same concepts of the search operation, and we will see this again. Obviously, the search operation is one of the most important functions in the binary search tree. The performance relies on the shape of the tree. So you can see that if this is the shape of the tree, we basically can guarantee to find the elements by compare once, twice, 3, 4. The worst case scenario is not found, so we need to look one layer down to see the null value. And this will give us a very good performance, and that's something that we are interested in. However, if the tree shape looks like this way, this is basically a linked list. It's not a tree at all. So the performance of the binary search tree relies on the shape of the tree. To find the maximum and the minimum is actually super easy. All we need to do is that we look into the tree starting from the root. Think about this. How would you find the minimum item? all the nodes on the left side are smaller, so you basically try to go to the left side, until you find a node that does not have any left node. That means this is going to be the smallest element. The same thing, if you try to find the maximum, all you need to do is go to the right side until the node has no right child, and that gives you the maximum value of the binary search tree. Let's come back several slides to look into the example and make sure you see that property. Take a look of this tree. If you go to the left side, that gives you the node of 1, indicating is the minimum value. If you keep going to the right side, that will give you the maximum value. Same thing for this tree. If you look into the left side and 2 immediately does not have any left child, that means this must be the smallest element. Same thing, you will find the maximum elements over here. Node 8 itself is the minimum and maximum, basically. If you look into this extreme case, starting from the root, there is no left child at all. That means the root is going to be your minimum value. If you travel from the root to the right side, and that node has no other right childs at all, that means this must be your maximum value. So that's the concepts that you find the maximum as well as the minimum. So that you can see, to find the minimum and find the maximum, you provide the node that you want to search. If you want to find the whole minimum, the minimum for the whole tree, then you provide the roots into the parameter. So what it will do is it will keep searching for the left side. As long as the left side is not null, go to the left side until there is no node that is null, no node that is you can travel to. That means it's a null node, then that must be your minimum. So you return the minimum. Same thing, you go to the right side to find your maximum. So those are the basic operations to deal with the binary search tree in terms of search, finding minimum, and finding the maximum. The next video, we'll want to talk about how do we do insert and delete to make sure that the binary search tree after the operation still stays the binary search tree.